Hey guys, how's it going? And welcome to this tutorial on the working of scintillation counter. Now, before we head on into the working of the scintillation counter, let's be clear on some of the basic definitions and the terms that I'll be using. Scintillation is basically a flash of light produced in a material by the passage of a particle such as an electron, an alpha particle, an ion, or a high energy photon. And the process of scintillation is one of luminescence whereby light of a characteristic spectrum is emitted following the absorption of radiation, and the emitted radiation is usually less energetic than that absorbed. So let's say if your material absorbs like 500 keV of radiation, then the emitted radiation would not be 500 keV, but it would be less than that, and usually it is observed that it is rather much less than the absorbed radiation. And here is an example of some liquid scintillator glowing under the presence of radiation. Alright, so a scintillation counter is an instrument used for measuring such ionization radiation by counting the light pulses produced by the scintillator. So what we have here is our scintillation counter consists of a scintillator, which is right here. This is our scintillator. Then what we have is we have a photomultiplier, which would be this section from here to here. This would be our photomultiplier, and the purpose of this photomultiplier is to multiply the number of light pulses that we get, because we don't get enough photons from the scintillator, so we need some kind of a multiplier system to amplify the signal that we get from the scintillator. And then we have a lot of electronics connected to our scintillation counter to process the signal that we are getting. So without further ado, let's get into the operation of the scintillation counter. So here is a scintillator. When high energy photons or radiation is incident on it, it emits low energy photons. Now these low energy photons are made to fall on this photocathode of the photomultiplier tube. Now this is the photomultiplier tube, and it is a vacuum tube consisting of a photocathode, an anode, and several dynode stages. Now I will introduce the term dynode a little later on. So first of all, let's go back. So when the radiation falls on the scintillator, it produces low energy photons, which are then made to fall on the photocathode. Now the reason I'm calling it photocathode is because it is a negative electrode, and it is covered with a photosensitive material. So when these photons are incident on the photocathode, what they do is due to the photoelectric effect, they liberate photoelectrons from the photocathode, and these photoelectrons are made to pass through these focusing electrodes so that they are incident on another electrode called the dynode. Now there are several of these electrodes which are relatively at higher potential from the previous one. So let's say this one would be at 100 volts compared to the photocathode, then this would be at 200 volts, then 300, 400, so that they are relatively at a potential difference of 100 volts with each other. So these are the dynodes, and what happens is that when the photoelectron that is ejected from the photocathode, it falls on the dynode excuse me, it liberates several electrons, and these electrons are called secondary electrons, and the photoelectron that was liberated from the photocathode is called the primary electron. So this primary electron has enough energy that when it strikes the dynode surface, it liberates a few secondary electrons. Now usually this number is like somewhere from 4 to 8. So let's say 5 secondary electrons would be liberated at this dynode, then they would be attracted towards the next dynode, which is at a higher potential. And also one thing to note is that these dynodes are such position that these electrons are led to each other, like they are reflected from one dynode to the other. So they are sort of curved, and they lie in the path of the electrons. And since they are all at a higher voltage, so the electrons are accelerated towards the diode. So at each stage the number of electrons keeps multiplying, because each electron can now produce 5 or 6 more secondary electrons. So after several stages we have a lot of electrons, and usually they can multiply a single electron into a million electrons, so that is a lot of gain. Okay, so here is another schematic, or rather an animation showing the working of the scintillation counter. So the radiation strikes the scintillator, which produces scintillation photons, which then fall on the cathode. There is this red stripe over here, and this cathode, since it is photosensitive, liberates photoelectrons which are accelerated towards the diode, and this diode will eject secondary electrons which get multiplied more by into more secondary electrons over here, and so on. And you can see here that each of these diode is, there are several resistors over here, so the potential of each of the diode is higher than the previous one. And then what we do is, in the end, when we have a lot of secondary electrons in our photomultiplier tube, then when they fall on the anode, we measure the voltage of the pulse that we get at the end from the anode. So that's how we can, in principle, measure the amount of energy deposited to our scintillator. Now, one thing I forgot to mention was that when a high energy photon is incident on the scintillator, either a part of its energy is absorbed by the scintillator or the whole energy is absorbed, depending upon the interaction process that occurs. And there are usually 3 interaction processes, that is the photoelectric absorption, then the pair production, and the Compton scattering. So we will talk about all these interaction processes in detail in a separate video, maybe the part 2 of this video. I'll name that like that. So we will talk about those in detail. So what happens is, whatever is the amount of energy that is absorbed by the scintillator, the number of photons emitted by the scintillator is directly proportional to the amount of energy absorbed by the scintillator, and therefore the pulse that we get from our photomultiplier tube is also directly proportional to the amount of energy deposited to the scintillator. Now keep that in mind, that the pulse is not directly proportional to the energy of the incident photon, but rather it is proportional to the energy deposited to the scintillator, and the energy deposited may depend upon the type of interaction that that photon has with the material. So that's what I wanted to tell you, and here is a rather interesting table to look at. Now let me just talk about the cesium-137 source. Now what we know about this source is that it emits a gamma ray photon of energy 662 kilo electron volts. And what we know about our scintillator is that usually the scintillators have a very low efficiency, and sodium iodide, which we usually use, it has an efficiency of 12%, and it is considered to be a highly efficient crystal. So what this efficiency means is that when this much of energy, that is 662 kilo electron volt, is deposited to the crystal, only 12% of this energy will be emitted from the crystal as the scintillation photons. Now I told you earlier that it might not be the case that all of this energy might be deposited to the crystal, but for now, for the sake of this video, let's just consider that all of this energy is deposited to the scintillator. So from a scintillator with efficiency 12%, what we will have is, we will have only 12% of this energy converted into scintillation photons. So that comes at about 79 kilo electron volt. Now since each scintillation photon has energy of 3 electron volt, because Our sodium iodide scintillator emits radiation lying in the range of ultraviolet to the blue end of the visible spectrum. So the photons have energy of 3 electron volts usually. So dividing this 79 kilo electron volt by 3 eV, we get 26,480 scintillation photons coming out of the scintillator. Now another problem here is that the photocathode does not have 100% absorption rate. So let's say if it has an absorption rate of 75%, only 19,860 scintillation photons will be absorbed by the photocathode. So out of this number, only this number of scintillation photons is absorbed. And if the efficiency of the photocathode is around 20%, then it would then only 20% of these scintillation photons that it absorbed would be converted into photoelectrons that would be emitted into the vacuum of the photomultiplier tube. So the 20% of this number comes at about 3,972 electrons. So only 4,000 electrons are emitted when about 26,000 scintillation photons were incident on the photocathode. And if you consider a multiplication of factor of 10 to the power 8 for the diodes, then the number of electrons that we get at the anode is about 400 trillion. And if you multiply that by the charge of an electron, that is 1.6 into 10 to the power minus 19 coulombs, then you get a very small amount of charge. So even after such high amplification by the diodes and the photomultiplier tube, it is still not enough to have this charge be easily measured by any electronics. So we will need two more electronic components in our scintillation counter, that is the preamplifier and the amplifier. Now this video is getting kind of long, so I'll rather end this video now and continue about on the rest of the topics in the next part of this video. Alright, that's it for today. Thanks for watching and have a great day.